Hello there. Let us start off with our first chapter, that is sets, and this is the first class. Now, before I begin, let me just give you the idea. My classes will be exactly like this. I will be recording a class, uploading it on YouTube, and I'll send you the link. Now, this will be helpful in a way, more helpful than your online classes, because once you see it, means you can see it more than once, as many times as you want, because you may not understand a particular topic in one go. Then you can definitely come back whenever you want, and you can watch it to get your doubts cleared. So I prefer doing it this way, and so let us begin. Now, as we begin, this chapter sets is already something you have done in your previous classes. You already have some prerequisite idea on the topic. So I'll just brush through. I'm not going to take much time on this. So, what is a set? A set is a well-defined collection of items. So, what is the meaning of being well-defined? Well-defined means that all the items which are collected to form the set, they must have a unique relation. Unique relation means they must satisfy a common criteria. So that common criteria or the correspondence, that is called well-defined. So every member of the set, means every single item in that collection, they are called an element. And obviously the well-definedness is the unique correspondence or the similarity which all these elements have. Fine. Now, let us understand how a set is denoted. Now, we already know a set is denoted by the capital letters in English and also some Greek letters. For some special kinds of sets, we use the Greek letters as well. Then, a set can be represented in a roster form or in a set builder form. So what is a roster form? Roster form means if I enlist the elements of the set within 2 second brackets, that is the roster form. And set builder form, if I write the unique correspondence. So basically that is it. Roster form is when I am writing the distinct elements. Now here this is very important. Distinct elements in the sense you can't repeat the elements. If there are elements getting repeated, you only count them once. You do not take them more than once. Again, in the set builder form, the same thing you write, but in the form of a relation. So let us take example and understand. So the first example I have taken is A, that is equals to 1, 2, 3, 4, 5. So this is a set containing 5 elements, and this 5 elements, if I write in set builder form, I can write it like x belongs to n. Now what is an x? X is a general term, general element. It is the how the element is going to look like. Now it belongs to n. What is n? N is the set of natural numbers. So we know the set of natural numbers starts from 1, 2, 3 like this, and x is less equals to 5. So that means what? All the natural numbers which are less than or equal to 5. So definitely it satisfies the criteria. So both the set A in the roster form and the set builder form, they tally. And similarly, if I take the set B, which is A, B, C, D, and in set builder form, it is X, such that X is the first four lowercase letters of English alphabet. So yes, this is exactly what it is, small a, b, c, d. So roster form is when I enlist the elements, and set builder form when I write the correspondence. Fine. Then comes something called cardinal number or cardinality. So cardinality is like the number of elements in the set. Now let me be a little bit clear. Number of distinct elements in the set. So I need not mention separately the distinct elements, because when I am writing a set, I am already writing the distinct elements in it. So it is pretty much the number of elements present in the set. Now, in the first case, that is in set A, I have 5 elements, so the cardinality is 5. And in the second case, the cardinality is 4. Fine. Next, types of sets. The types of sets, the first one that we come across is a finite set. What is the meaning of finite set? A set having finite number of elements. So it is pretty much easy to see that if I take these two examples where I have 4 elements, so obviously it is a finite set. Infinite set, a set having infinite number of elements. Now for the example, N, Z, Q, R, these are examples of infinite set. So now first we need to understand what these symbols represent. N represents the set of natural numbers, Z represents the set of integers, Q represents the set of rational numbers, and R represents the set of real numbers. So like right from class 6 till class 10 you have learned all the different number systems. So you started off with natural numbers in class 6, then you came up in class 7 and learned integers, then in class 8 you learned rational numbers, then 9 irrational numbers, and all together in class 10 you learned the idea of real numbers. So pretty much that is the hierarchy. First comes natural number, then comes integer, then comes rational number, then irrational numbers, and then real numbers. And in class 11 we are going to study another set of new kind of numbers called complex numbers. So all these sets, they represent an infinite set of numbers obviously. And for example, if I take the set of natural numbers, you can see natural number is like 1, 2, 3, 4 and so on, it goes on. So it is an infinite set. Now you may ask one small question, that what about the cardinality or cardinal number of an infinite set? So obviously that is something which is beyond our scope of discussion, but there is a concept of cardinality of infinite sets, but we don't need to discuss on it. If you want, you can always go and search on YouTube or on net, and you can find out that whenever we have infinite sets, the cardinality of infinite sets are basically the cardinality of the smallest infinite set, and it is compared. So there is a huge theory on that, so let us not go deep into it. Next, an empty set. What is an empty set? A set having no elements at all. So a set which doesn't have an element means there will be, in roster form, I can represent it by putting 2 empty brackets, I mean 2 double parentheses or second brackets, and I don't write anything in between. Or there is a obvious symbol for it, that is phi. And also you can write it in set builder form by defining a correspondence which doesn't satisfy any criteria. For example, if I take this A is x belongs to R, that means x is a real number such that x is square root of x square plus 1 equals to 0. Now obviously this is an empty set. This is an empty set. Why? Because I know there is no real number for which x square plus 1 is equals to 0. Because if I take x square plus 1 is equals to 0, that means x square is equals to minus 1. Now if x square is equals to minus 1, I know no real number when squared gives you a negative number. So therefore no such real x exists, and hence the set A represents an empty set or null set. Fine. Then again, if I take B is equals to x belongs to n, x is a number on a fair die, and x is greater than 6. So obviously a fair die has got 6 surfaces and it has got 6 numbers 1, 2, 3, 4, 5, 6, and I am looking for a number on a fair die which is greater than 6. Again, that is impossible. It is not possible. We don't have a number greater than 6. So therefore, this is also an example of null set. So you can define a null set in several number of ways by putting a correspondence which does not satisfy or which is invalid. And then finally I have a singleton set. What is a singleton set? By the name it suggests that singleton means there is only one element in the set. Now obviously this is something, a point to be noted. This set and this set, they are different. Why? Singleton 0 means 0 is still considered an element. So don't think that 0 means there is nothing in it. 0 is still an element inside. So singleton 0 is pretty much a non-empty set. But when I am writing two empty braces, that is representing an empty set or null set. So these two are very different. So 0 need not necessarily, 0 does not mean, not necessarily, 0 does not mean that it is null, because 0 is still a value. Fine. Next, equality of sets. Now this is also something you have done previously. When do we call two sets to be equal? Now before we discuss equality, when do we call two sets to be equivalent? Let us understand that. So two sets A and B are called equivalent if the number of elements in the set are equal. So we can see, I have taken an example. A is 1, 2, 3, B is A, B, C. Now obviously A has 3 elements, B has 3 elements, so they are equivalent. Fine. So equivalence is the equality of number of elements, not the elements themselves. Be very careful, and you have a notation for it. Next, when I say them to be equal, well, obviously if not only the number of elements but the elements as well are equal. Now obviously the order of the elements is not important in a set. It is definitely not important how you are writing the elements. You can write the elements in any order you want, but still they remain equal. So therefore, if I take 1, 2, 3 and 2, 3, 1, two sets, now these two sets, they are equal because the number of elements are equal and as well as the elements themselves are equal. Doesn't matter in which order they are, right? So from here you can deduce one thing, that all equal sets are equivalent, but definitely not the other way. So next, subset. Now from here the theory goes a little bit different because you haven't done subsets previously. You may have idea, but definitely you haven't done it previously, I'm sure. So what is a subset? Now by the word subset you can understand subset, that means part of a set. So if I take two sets A and B, then B is called a subset of A if every element of B is an element of A. So that means, let me just give you an idea. Now something called Venn diagram, you have done it previously. Now in Venn diagram, if I am drawing this set A, if this is my set A, and if I am drawing another set B inside, so that means what? B is already inside A, so that means any element of B is always an element of A. So therefore B is called a subset of A, right? Now obviously the other way around, you can also say A is the superset of B. Now generally we don't use the superset concept much, means we don't visualize the sets in the form of supersets, but we visualize them more in the form of subsets. So here we will be sticking to the subset notations, not the superset notations, until and otherwise we require to. Fine. Now obviously if I am taking the example A, which is 1 2 3 4 5 6 and B is 2 3 5, then I can obviously see that all the elements of B are actually in A, and hence I can say that B is a subset of E. Fine. Next. Now this is very important. Null set or empty set is always considered to be a subset of any set. Why? Because whenever you are taking a null set means you are not taking any element out from the set. So therefore it is obviously can be considered as a subset, and obviously the whole set itself is a subset. Now that is pretty obvious. If I am taking A, now all the elements of A are actually in A. So going by the definition of subsets, I can definitely say that A is subset of itself. It is pretty much like writing, say for example, I can always write 5 is equal to 5. Say for numbers, I can always write 5 is equal to 5. At the same point of time, I can write 5 is greater equals to 5. Or I can write 5 is less equals to 5. It is a true statement. Why? Because when I am writing 5 is less equals to 5, that means what? 5 is either less or equal to 5. So therefore, the equality concept is already embedded inside that less than or equal to. So therefore, if I write 5 is less equals to 5, then it doesn't harm or it doesn't stand false. So therefore, in similar way, I can say that A means a set is a subset of itself. Right? Next. Now let us consider a few sets here. A is 1 2 3 4 5 6 7 8 9, B is 3 6 9, C is 2 4 6 8 10, and D is X belongs to n, X less than 10. So I have taken these 4 sets. Now obviously we can see it that B is a subset of A. Why? Because all the elements of B are in A. Then C is definitely not a subset of A. Why? Because there is one element in C which does not belong to E. Now if I find at least one element which does not belong to the parent set, then definitely I can't say the set to be a subset. So here C is definitely not a subset. Next. Now see this, D is a subset of A for sure, because D is pretty much exactly equal to A. So therefore we can say that D is a subset of A as well as D is equal to A, and hence I can write D is a subset and equal to A. This is more like greater than or equal to or less than or equal to. So this symbol is used to represent a set which can be a subset or which can be equal to a set. So therefore this is a combination of a subset symbol and an equality symbol punched together to form this symbol. Fine. Next. Now on basis of the symbol, we differentiate a subset in 2 categories. The first one is called a proper subset and the second one is called an improper subset. Now what is a proper subset? Proper subset means that it is contained completely inside the set, right? And improper subset means it can be equal to the set also, right? And also a null set can be considered as an improper subset as well. So this is basically that is what it is written. Any subset of the set which is completely inside the set, that is called a proper subset, and it is denoted by that only the symbol, no equality sign there. And in case of an improper subset, a subset which may be equal to the set or a null set. So null set is an improper subset and the set itself is an improper subset, and it is denoted by this symbol. Now obviously the usage of symbol is different in different books. It matters from book to book. Many books prefer to use the first symbol, many books prefer to use the second symbol. So it definitely doesn't make difference. Now obviously this symbol is more generic in the sense, if even if it is a proper subset, you can use this symbol, no problem with that. Why? If it is a proper subset, now B is a subset of a proper subset or not doesn't make much difference, because definitely this symbol contains both the logic. Either it is a subset or it is equal to. So in one of the logic it definitely satisfies, right? It is more like less than equals to or greater than equals to. So just keep that in mind, it will be easy for you to understand. Okay, next. Now let us take a set 1, 2, 3. If I have taken this set 1, 2, 3, let us list all the different subsets of the set. Now see, understand this very carefully. If I have taken the set A, which is 1, 2, 3, and I am listing all the subsets of the set A. Now first, null set, obviously null set is a subset, so that is done. Null set is a subset, right? Then singleton 1, so if I take only one from the whole set, then that is also a subset, right? It is gone. Next, singleton 2, done. Singleton 3, done. Then I have already taken single element once, so next I have to take two elements. So if I take 1 and 2, that is also a set. 2, 3, 1, 3. So I have taken all the elements 2 at a time, and finally I am left to take the whole set itself. So therefore I can see a set having 3 elements has got 8 subsets. If you just count, there are 8 subsets, right? Now how do I get the subsets? I mean, how do I get all the subsets? By listing the elements, taking 1 at a time, taking 2 at a time, taking 3 at a time, and so on, right? So you have to take all possible combinations of the elements and you have to create the sets, right? Now if you see, obviously the null set and the whole set, they are the improper subsets as by the definition, and rest of the sets, they are proper subset because they are contained completely inside the set. Now how to correlate the number of elements of a set, that is the cardinal number of the set, with the number of subsets of the set. So you can see, what is the cardinal number of the set? It is 3. And what is the number of subsets of the set? It is 8. So how I can correlate 3 and 8? See this, how I can correlate 3 and 8? Obviously I can correlate 3 and 8 with this. 2 to the power 3 is equals to 8. So that means what? If I have n number of elements, whatever that n be, if I have 10 elements, if I have 12 elements, if I have 5 elements, doesn't matter what, then the number of subsets will be 2 to the power of that, right? This is what the generalization is basically. So you can take any set for the matter of fact, and you can try listing all the subsets. So now take 4 elements, try listing their subsets. So now you understand already that if I take 4 elements, there will be 16 subsets. 1, 6, 16. So therefore it will be a big list of subsets, but you can obviously try and check. Next, the idea of power set. Now power set is basically the same idea but in a different form. Now what is a power set? Power set is the set of all subsets. Now instead of listing them separately, if I list them inside a set, that is called a power set. So if I have a set capital A, then the power set of A is denoted by script P, A. Now obviously this script P is completely unnecessary. You can just write PA as well. No problem with that. It is a fancy notation, so it's just your choice how you want to represent it. Now obviously for the previous example that I have taken, that is A equals to 1 to 3, obviously the power set is exactly the same set, the same list of subsets, but inside a set, right? Now, once I understand that power set is actually collection of sets, means it is a set of set. So that is very important for us to understand. That means what? What is the meaning of set of sets? Set of sets means that every single element of a power set, they are actually a set. For a normal set, each and every single element of a set is any number, any letter, it can be anything. But for a power set, each and every single element, they are set in itself. So this is a very important revelation, or it is a very important understanding which you have to make. So once we understand this, once we understand the fact that power set is actually a set of set, then there are so many different things that happens we need to understand. The first thing is that if I write 1 belongs to power set of A, it is wrong. Why? Because 1 is just a normal element. So a power set cannot contain only elements, right? Because it is a set of set. So instead of writing 1 belongs to power set of A, I have to write the set, singleton set 1 belongs to power set of A. So do understand this very carefully. This is very important. It can be confusing a little bit, but do understand this carefully, that power set is a set of set. So all the elements of power set, they are set in itself, and hence no normal elements can be a part of the set. Anything that has to be part of a power set, they has to be in the form of a set. So therefore I can write singleton 1 belongs to power set of A, not only 1, right? Once again, if I want to write the singleton 1 belongs to A, obviously it is wrong, because the set cannot belong to the set A. The singleton set cannot belong to the set A. Why? Because A is a normal set, it contains elements which are normal numbers. So A cannot contain A cannot contain a set. Well, that's how A is defined. So therefore what we can write? We can write the set 1, the singleton set 1 is actually a subset of A, right? Because that's what the definition of power set is. Power set is the collection of subsets of a set. So therefore singleton 1 is actually a subset of A. So please be very careful with the notations. This kind of questions are there where you will be given a set, its power set, and some other elements, some other sets. You will be asked if the statements are true or false. So obviously remember this, that power set is a set of set. So all the elements will be a set in itself, and a normal set is just a set containing normal elements but not set. Then let us come to something which you have done recently in the sense, I think you have done it in class 10, I don't know, must be in the chapter of linear inequalities. Now if I have two real numbers, A and B, and let me take B to be greater than A, then I can generate 4 different types of subset. And all these 4 different types of subsets, they are called intervals. Fine. Now how these 4 different types of subsets can be? The first one is X belongs to R such that A less equals to X less equals to B. That means what? It is all the elements between A and B taking A and B also. So when we represent this on the number line, how do we represent? We represent it like this. if this is a number line and A and B are the 2 points on the number line, then I consider both A and B and anything in between. I consider A and B and anything in between. Now obviously I didn't get a chance to mark the whole thing, so just understand I am considering this whole interval, the whole interval between A and B, right? Now the next one, x belongs to R, A less than x less equals to B. So it is again, I am considering the elements or all the real numbers between A and B, considering B but not considering A. So it is something like this. Easy for us to understand. This is something we have already done. Next, the same thing but the other way around, considering A but not considering B. And the last one, considering neither of the two. So we are not considering the endpoints but all the elements in between, right? So these 4 types of subsets, obviously first we need to understand that these are subsets of real number set. Obviously yes. Why? Because all the elements of these sets, they are real numbers. We are sure of that. So therefore this is a subset of the real number set. Now they have names. We need to understand what the names are. The first one, that is A less equals to x less equals to B, that is considering both the endpoints, they are called a closed interval. If I consider both the endpoints, they are called closed interval. If I consider one of the ends, now here there is a little bit notation differences from book to book, it differs. Now if for I am kind of denoting that if I consider the right endpoint, then I will be calling it a semi-closed interval. Now in some book you will find that this is called semi-open interval also, but I am doing it the other way. If I consider the left endpoint, I am calling it as a semi-open interval. Now these two can be changed. I can consider anyone as semi-open, anyone as semi-closed, so no problem with that. And the last one, when I am not considering both the endpoints, I call it an open interval. Fine. Now they have a notation. Notation means they are written in a compact form. Now this compact form, the first one, it is written as AB within third bracket. The third bracket represents closed interval, right? Semi-closed, obviously the side which is closed will be a third bracket. The side which is open will be a first bracket. So this is called a semi-closed interval, right? Next, semi-open interval, obviously the idea is clear by now. The side which I will consider will be a third bracket. The side which I am not going to consider will be an open bracket. And finally, an open interval will be both in single bracket. Your first brackets. Fine. So these are the interval notations. So previously you may have to write the solution set for inequalities like all these big sets, but instead of writing like this, you can always write in the interval notation, so it makes the whole thing a little bit more compact. Now, universal set, a set which is considered to be the superset of all the sets in a particular problem. So this is the idea which we will be able to understand when we solve the problems like it. Now definitely these problems will come a little bit later, not in this exercise that which we are going to do. So when we will be dealing with the universal set problems, then we will understand what it actually means. But for a rough idea, what we can understand is that, so let us consider a problem given where A is 1, 2, 3, 4, 5, 6, 7, 8, 9, B is 3, 6, 9, and C is 2, 4, 6, 8, 10. Now I need to find a set which can be considered as a universal set. Now understand what is the meaning of universal set. Universal set means it is a set which can be considered as superset of all these three sets, right? Now obviously if I take the set of natural numbers, then it is definitely an universal set for all these three sets, no doubt. But whenever we are talking about universal set, we talk about the minimal set. Minimal set means the smallest set which I can consider that will be the superset of all the three sets. So here if I take, now obviously universal set is denoted by capital U or xi. This is called the xi symbol. So if this is the xi symbol, if I have these three sets given A, B, C. Now if you see, if I define my xi in the form 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then is it not clear for us to see that A is a subset of xi, B is also a subset of xi, C is also a subset of xi? Or in other way around, I can say that xi is the superset of all these three sets. So therefore this xi can be considered to be a universal set. Fine. Now once we have understood the concept of universal set, so in this class what did we do? First we discussed what is a set, then we discussed what are the types of set, or first how the sets can be represented, then the types of set, then we discussed what is the cardinality of set, means the number of elements of a set, then we discussed subsets and the types of subsets. We have a proper subset and improper subset. Then given a set of elements, how many subsets there can be, and obviously the concept of power sets. And after the concept of power sets, obviously what is a power set? Power set is a set of set. So therefore the idea of notations will be a little bit different. That also we have discussed. And finally in between we have also discussed the subsets of a real number. Subsets of real numbers are called intervals, and there are 4 different types of intervals. And finally we have discussed universal set. So this is today's class, and let us just go through few sample problems. Now obviously these are the problems which I think I need not solve, because these are very simple exercises which you can do it all by yourself. But still, let us go through few problems. Problem number 1, write the following set in roster form. You have done it before. So this is the first one, x such that x belongs to n and x is a prime factor of 84. And the second one is the set of all letters of the word trigonometry. I think I need not tell you how to do this. So first one, x is 2, 3, 7. Now if you just go through the different factors of 84, you will find that there are only 3 prime factors of 84, that is 2, 3 and 7, right? Next, trigonometry. Now obviously I have to enlist the distinct letters being TRIGONMEY, and that is the set. Done. Next, problem number 2, write the following set in set builder form. Now it is just the opposite question. The first one is 2, 4, 6, 8 ... that is an infinite set, and the second one is half, 2/3, 3/4, 4/5 and so on. So the first one is very easy for us to see, that x such that x is a even natural number. 2, 4, 6, 8, these are all even natural numbers, so definitely I can write that in set builder form. Next, the second one I can write x such that x is equals to n by n plus 1, where n belongs to n. So what does this mean? This is a little bit something we need to discuss. X is the general element structure of the set, and how the structure is, it is a natural number divided by its next natural number. So that's how the set is formed. So therefore this is what the set looks like in set builder form. Fine. Next, number 3. Classify the following set as a finite or infinite set, and if finite, write the cardinal number. So first one, x equals to 5n, where n belongs to I. I is same as z, that is the set of integers, and x is less than 20. Fine. And the second one, x is an even prime number greater than 2. So the first one, if you can guess right, then it is definitely an infinite set. Why? Because the set of integers, they extend infinitely to the negative side as well. So if I write x is less than 20, obviously it doesn't matter if x is less than 20, but it will go on and on to infinity in the negative side. So therefore it is an infinite set. And also I have written how the set looks like. So it will start at 15, 10, 5, 0, minus 5, minus 10, and so on. It will go on. Next, the second one is obviously it is finite, no doubt about that. But moreover, it is a null set. Why? Because you are asked to write, or you are asked to write the set containing even prime numbers greater than 2. Now obviously we know there is only one even prime number, and that is 2. There is no other prime number which is even. So except 2, all the prime numbers are odd, and therefore this set doesn't contain any element. So it is definitely finite. It is rather an empty set, and hence its cardinality is 0. Fine. Last problem. Write the following sets as intervals. Now you will be given some subsets of real number, and you have to write it in interval notation. So the first one is x belongs to R, minus 3 less x less equals to 5. Now if you just go through this is the closed interval, and then the next one, x belongs to R such that x is greater or equals to minus 2. This is a semi-open interval. So the first one can be represented something like this, minus 3 comma 5. Why so? Because minus 3 is not included, 5 is included. Simple for us to see. But in the second one, we can see it is given only one side of the limit, not the other side. It is written that x is greater or equals to minus 2. So x is greater or equals to minus 2 means that it is starting from minus 2, but it is going on and on and on. It is never ending on the other side. So therefore on the other side there will be infinity, right? So it will be written something like this. Now we need to understand this, that infinity is a concept, it is not a number. Infinity is a concept, it is not a number, and hence whenever we are going to write infinity, we are always going to write open bracket. That is the first bracket. We will never put a third bracket. Infinity doesn't represent a number. What is actually infinity? Infinity is a concept which tells us that whatever number I can consider, whatever the large number that I can consider, I can always get a number bigger than that. That is infinity. So if I take 100 zeros, then 100 zeros, if that I consider as the largest number I can think of, then I can obviously write 1, then put 99 0, and then put another 1. So that makes a bigger number. So you can never think of the largest possible number. So there is no concept of that. And hence infinity just represents that concept. Right? So that's it. That is our class. So thank you so much. We will be meeting in the next class where we continue with the chapter. But definitely before we move to our second class, it is advised that you people don't rush with your class 11 syllabus, because we have time, and also you have to ensure that you go through your leftover exams, leftover subjects of your ICSE board exams. So give yourself some time, go through your ICSE subjects. Obviously that is your priority, and along with that give yourself some free time to go through these things as well. So take your time, we will be meeting in the next class. Thank you.